Alright, so now we're going to look at this method that I've alluded to in the past lecture in section 6.2. And this method is called cylindrical shell method, right? It's another way for us to calculate volumes of solids of rotation. Let me show you when we use something like this, right? So suppose we want to find the volume of a solid given by rotating the region bounded by the following equations about the y-axis, right? So I'll try to use the colors we've been using, right? So we're rotating about this axis. So then our slice is going to look something like this, right? And immediately we know this is going to be a washer because of this gap here. Okay. Well, we know what our lower limit is for the integral. Our lower limit is going to be 0, right? That's our smallest y value down here. Okay. And our upper limit is going to be whatever this vertex looking point is right here. Well, we know we're going to have a slope of 0 there. So I could take y prime, which would be 4x minus 3x squared. And I could set this equal to 0. Let's see. And if I factor out an x, we'll get 0 equals x times 4 minus 3x. So we know that x is either equal to 0, which, if x is equal to 0, that would be somewhere on this axis right here, right? In fact, it would be this point. Or the point that we're looking for, which is going to be x equals 4/3. Okay, and that comes from solving this portion of the equation when setting it equal to 0. So I can get this upper limit. This is 4/3. This is a little bit of work so far, but not too bad. I mean, not completely unreasonable. But this is what's going to be difficult. When we're looking at our inner and outer radius, right? So here's our inner radius, here's our outer radius. What I need to do is I need to break this function up to where I'm splitting it at this vertex. What I mean by splitting it at the vertex is I want to know the function that only accounts for this part of our curve so that I can get our inner radius. Okay. This is going to be difficult because we're going to have to start writing 2x squared minus x cubed in terms of x. So we're going to start having to look at our solutions to a cubic equation, which if you Google that and look it up, it gets really nasty. And this is honestly not even one of the worst scenarios. We could start looking at solutions to quartics or quintics, and it's just going to get ridiculous. So instead what we're going to do is we're going to try this thing called the method of cylindrical shells. What the method of cylindrical shells would let us do is that instead of taking our slice perpendicular to the axis of rotation, if you imagine purple as being the color of our slice, we could take it parallel to the axis of rotation, right? And so now I'm going to get something, right? We haven't talked about what the formula is yet, but I can clearly see this is going to be an integral from 0 to 2. I can tell what my top and bottom curves are, right? This is it's going to get a lot easier. So a situation like this, where you're trying to use disk or washer, right, and you've got these nasty functions, this is a time when you're going to want to use cylindrical shells. Now, let me firmly state that cylindrical shells is not like the is-all-be-all solution to volumes of solid revolutions. There are times where it is very unhelpful to use the cylindrical shell method, and we're going to run into one of those. Okay, so now let's talk about this. So the method of cylindrical shells, we calculate our volume by setting volume equal to circumference times height times thickness, right? And we can rewrite this as an integral depending on which axis we are revolving around. And this is something I want to make very important. That is, for cylindrical shells, your cross section, your slice, right, will be parallel to your axis of rotation. Then we can start looking at what the integral formula is. If you're revolving about the line x equals c, and so what I mean by that, that's going to be a vertical line that we're revolving about. C is just some number given to us to use, like x equals 0, or x equals 2, or x equals -3. Then we're going to use this formula. Where this absolute value of x minus c comes in is kind of like when we were calculating our radii for the washer method. It's just making sure that we get a positive number right there. We'll talk more about that when we look at it in different cases. A and B we're still going to get from finding the smallest and biggest x values in the region, and f of x will be our top function, g of x will be the bottom function. So let's go ahead, let's practice this, maybe just setting it up on the problem above, right? So this is supposed to be the integral from a to b of 2 pi times the absolute value of x minus c times f of x minus g of x, where f of x is the top function, g of x is the bottom function. Let me make sure I put a dx in there. I did. Yay me. Okay, we already found a and b. Then we're going to have a 2 pi. And then this absolute value of x minus c. What is this? Okay. In this scenario, we're revolving about the or the y-axis. So our axis of rotation is going to be x equals 0. So here's what I want to mention. If I take a point on, now I'm going to extend the screen curve out. If I take a point on the screen curve, it's going to be bigger than 0. So I'll always want to do the point on the curve minus 0 when we're looking at x values to get a positive number. Okay? Now, that's why we're going to do, it'll be the absolute value, instead of absolute value of x minus c, it's just going to be x minus c. Let me try explaining that again. Let's suppose we had some, I don't know. Let's do this blue. Let's say instead our curve looked something like this, right? And we were going to use the method of cylindrical shells. And we were trying to figure out how do we write our absolute value of x minus c part. Well, on here, if I'm taking values on here, points on here, then our x values are going to be smaller than 0, right? They'll be negative. So I'll want to do 0 minus those x values to get a positive number. So in that case, I would have c minus x. And in both of these scenarios, right, we already know what our c is. It's given right there. So c is going to be 0. Okay. And I'll keep on going over this as we see more examples, so hopefully it starts to make more and more sense. And then it's going to be top minus bottom. Well, that's going to be our f of x function. So 2x squared minus x cubed is the top function. And then the bottom function is given by this y equals 0. So then minus 0, so nothing there. And then dx. So now all I'd have to do to find our volume is pull this 2 pi out, distribute our x, and then the integral, it's really not that bad. We can just use power rule on 2 separate parts. Okay, and so this is an example of the method of cylindrical shells, just making things a lot easier. Okay, Similarly, if we're revolving about a line that's y equals c, right? So if we're revolving about a horizontal line, then we would have basically the exact same formula, except for now a and b are found by giving our smallest and biggest y values in the region. This absolute value y minus c is going to work very similar to our absolute value x minus c. And then f of y minus g of y, that would be our right function minus our left function. Okay, so let's take a look at this. Find the volume of the solid given by rotating the region bounded by the following equations about the y-axis. All right, so we'll have green and blue. And so we'll have, let's see, our graph. This is going to be, let's see. First, I need to rewrite this green equation so I can get a better idea for what it looks like. So this will be y equals negative x minus 1 squared plus 1. And this I went over in the last video of how to complete the square. That's what I'm doing here, is completing the square to get this equation. Okay, so this is a downward facing parabola that's been moved right 1 and up 1. Okay. So it looks something like this. All right. And the blue line is going to look like this, right? That's our y equals 0. And we are revolving about the y-axis. Okay, so we're taking this region in here and revolving it about the y-axis. So similarly, we're not going to do a washer method, because if we do washer method, we're taking a slice like this. So not only do I have a dy integral, which means that I need to turn our green function to where it's in terms of, x equals something with y's in it. Not only that, but we'd get a square root, a plus or minus square root, which means I'd actually have to break up the plus and minus right here so that we could start looking at different integrals, right? If you want to try to set up the washer method, you're more than welcome to. I personally don't recommend it. So let's look at how does the volume by cylindrical shells method work here. Okay, so let's restate our formula. Since we're revolving about a vertical line, right, something that looks like x equals something, right? Ours is x equals 0. Let me go ahead and write that real quick. We're revolving about x equals 0. So we're revolving about a vertical line, which means that our volume should look like the integral from a to b of 2 pi absolute value x minus c. Whoops. And here I'm going to replace our c with what we've been given. We're given x equals 0, so our c should be 0. Times f of x minus g of x dx. Okay, so I can get a and b. That's going to be our smallest and biggest x values. So that should be 0 and 2, given by these 2 points right here. And now let's think about it. Okay, we have x values on this green curve. They are always greater than or equal to 0, right? Because they're to the right of the y-axis. That means if I take some random point on this green curve that's bounding our region, then we would want to do that point's x value minus 0 in order to get a positive number. For instance, if I take this point right here, I don't know what it is, but it's maybe approximately 1.5 comma some y value. And so if I wanted to get its distance from our axis of rotation, right, if I wanted to get this distance, then what I'm going to do is 1.5 minus 0. So that's why I'm saying that we should have x minus 0 right here instead of 0 minus x. So this is going to be 2 pi x minus 0, right, which I'm just going to write as x, times, now we'll have the top function, which is 2x minus x squared. Notice I've got two different ways I can write it. I've got this way and I've got this way. I'm choosing the former because it's a lot more simple to integrate, right? They're both equal to the same thing. I'd just rather integrate this one right here as opposed to the other one, right? And then we'll have minus g of x. Well, our bottom curve is that y equals 0 curve. So we'd have minus 0. So I can get rid of that. And then we'd have dx. And so just like the last video, I'll work this integral out. But I feel like once you get the integral set up, the rest of it isn't as bad, right? It's figuring out what method you should use and getting the integral set up that is usually the hardest part here. But I'll go ahead and calculate this first one out. So this should be 2 pi times the integral from 0 to 2 of, let's see, so I'll distribute out my x right here. So this will be 2x squared minus x cubed dx. So this is 2 pi. We'll integrate, so this will be 2x cubed over 3 minus x to the 4th over 4, evaluated from 0 to 2. Now, I can do a trick here, right? I could do this. I can write this as, what I'm going to do is I'm going to multiply, it's a little too late now. I'm not going to do it. What you could have done, you could have noticed that this region right here is symmetric about this line. So we can change this to 2 times what we have, except for we take our limits to go from 0 to 1 instead of 0 to 2. Right, so what I'm saying is right here, I could have rewritten this as 4 pi times the integral from 0 to 1 of 2x squared minus x cubed. It's not a big deal right here. 2's not a bad number to deal with, but it does make things a little bit easier. Okay. And so then this will be equal to 2 pi times 16 over 3 minus 16 over 4, which will give us 8 pi over 3. Okay? And so just like I said, in the future for the rest of these problems, I'm probably going to stop once we get the cylindrical shell method. Right? So if I ask you on a quiz problem or exam problem, set up but do not evaluate the integral using some method, what you're looking to do is get right to this point right here. Here, we have used the cylindrical shell method to set up an integral, and you wouldn't need to evaluate from there. However, I'd say, maybe not on an exam because you don't want to waste the time, but on the rest of these assignments, even if I give you something like that, try to evaluate it if you can. If you can't evaluate it, bring it to me, and I'll either show you what trick you're missing, or I'll tell you that we just haven't learned how to do something like that yet. Okay, now let's look at example 2. So we're going to have some new curves bounding our region, and we're going to be rotating about, I'm going to change this real quick to the y-axis. Just so that you'll see if we do the x-axis, then we don't really get to practice our cylindrical shell method. Or at least, maybe not in the way that I want us to right now. So, let's look at this. So we have green, blue, and purple for our curves. And I'm going to rewrite this purple curve as y equals negative x plus 2 so that we can get a good idea of what everything looks like. Okay. So we should have something that looks like, let's see. Let's start with y equals 0. I like that one. Nice, fun line to draw. Y equals negative x plus 2. So that means we have a y-intercept of 2. And then it's going to look something like this. All right. And now we need to look at y equals square root of x. So it's going to look something... Oh, that's nice. We're already going to get a nice point there. If I want to finish this out, then it looks something like this. All right, so we're looking at this region right here. And we're going to be rotating about the y-axis. So this is x equals 0. So then our integral should be the integral from a to b, right? Because notice we're going to be taking vertical slices. And then we should have, this is v equals the integral from a to b of 2 pi times the absolute value x minus c times f of x minus g of x. Okay. Here, we're going to have to split this up. Here's the reason why. For one, f of x minus g of x, that's top minus bottom. However, if we look at these two slices, they have the same bottom function but differing top functions. Also, if I want to do absolute value of x minus c, am I taking a point on the green curve or the purple line? Right? We could be taking them at either place, and so I can't give you one function that's going to represent the distance from the y-axis for a point that's on either curve. So what I'm going to do is I'm going to split this up into, let's see, we're going to call this the left section, and we'll call this the right section. All right, so let's look at the left section first. This would be v equals the integral from, well, let's see, so it's going to be the x value right here and the x value right here. So this should be the integral from 0 to 1 of 2 pi. We're to the right of our axis of rotation, which means that it's going to be x minus c and not c minus 0. So we have x minus 0. And I guess that's maybe even a better way to think about it. If you're if you have a vertical line that you're rotating about, if your curve sits to the right of that line, then you're going to be doing x minus c. If your curve sits to the left of the line, right, if it looks something like this, then you're going to be doing c minus x. Okay? So now we'll do top minus bottom. Oh, this should have a dx on it. So we'll do top minus bottom. That's going to be square root of x minus 0 dx, right? Because we're on the green curve and the blue curve. All right, and then so we've set it up using the cylindrical shell method. And notice here, all we're going to do is pull out 2 pi. We'll multiply x and square root x, integrate it with the power rule, and then evaluate. And that would give us 4 pi over 5. Now for the right-hand side, we will have v equals the integral from, so now we're going from 1 to, so this should have hit more right at like this point right here. So it should be going from 1 to 2, right? If your graph isn't perfect, then another way to do that is we take our equation for the purple line, which was negative x plus 2, set it equal to 0, and you'll see that x equals 2 is the solution to that. So that's why my upper limit is 2. So it's the integral from 1 to 2 of 2 pi times, right, we're to the right of our axis of rotation. So it's going to be x minus 0 instead of 0 minus x. And we'll have top minus bottom. So that's going to be, our top curve is negative x plus 2 minus the bottom curve, which is 0, dx. Now, this one, we'd pull out our 2 pi, distribute out, and then we'd have 2 power rules to integrate and then evaluate afterwards. When we do that, we would get 4 pi over 3. And so then our total volume is going to be 4 pi over 5 plus 4 pi over 3. And this will give us our total volume, right? We can add from there, get common denominators to get an official number, but this is all we need. Okay, now we'll move on to example 3. For example 3, now we get to revolve or rotate about something that isn't just the x-axis or the y-axis. So here, just like on the last video, I'm going to kind of, I guess you'd call it, over-accentuate and go by 0.25 instead of 1 like we normally do. And remember, that's so that we can get a good view of what's going on in this region and where we're where the gap is that we're rotating. So let's see, if we have, this is y equals x squared, this is going to be y equals x. Y equals x would be something like this. Y equals x squared. So let's see, we'd have a point right here for sure. This would come here. Then we'd meet back up again here. So something like this, approximately. So then our region is in here. All right, and then to get an idea, this isn't exact at all, but this would be where we're rotating about, right? This line at x equals 3. And so again, since we're rotating about a vertical line, and we're going to do a cylindrical shell method, our formula should look like v equals the integral from the left bound to the right bound, so 0 to 1, of 2 pi times the absolute value of x minus c. So now notice that if I take a point in this region, right, say something like this, that's maybe something like 0.6 comma whatever the y value is. then the distance from this point to this line would be 2.4. And the way I get that is by doing 3 minus 0.6. So our absolute value of x minus c here we have that 3 is going to be our c, because this is x equals 3. So since I'm doing 3 minus 0.6 to get that distance, right, because we want a positive number for our distance, then this needs to be 3 minus x. Then we'll do top minus bottom, so that'll give us x minus x squared dx. And so here the goal would be to pull out the 2 pi, FOIL these out, and then integrate. And when you do, you'll get 5 pi over 6. And so I really like this, even if a washer is convenient, because let's say we decided to do the washer method, right? Now I'm going to do a slice like this. So I've got to account for my outer radius, my inner radius. It's going to be a dy integral, so this function right here needs to be rewritten as plus or minus square root y equals x, which isn't too bad because we can use just square root y, since the positive one will account from here, all the way in this direction, right? It's going to account for the part of our curve that's in quadrant 1. Right, but it's still a pain to have to do that, and then our integral is not going to be as nice. So I still think even here, where washers are reasonable to do and possible to do, I still think that the cylindrical shell method is a little bit faster. Okay, now let's look at example 4. And so I think you can already tell that this video is going to be a lot shorter than the other video. That is, so long as example 6 doesn't take the 30 minutes to an hour that it could take. Okay, here I'm going to be rotating about x equals -1. So I'll go ahead and mark that. So it's this line right here. X equals -1. That's what I'm rotating about. And then our region should look something like, okay, so we've got the lines y equals 5 and x equals 1. Those aren't too bad. 1, 2, 3, 4, 5. So if I mark this as green, blue, and purple, I can go ahead and start making some of these. Alright, and then y equals square root x plus 2. So let's see. If I plug in 0, we'd get 2. If I plug in 1, we'd get 3. If I plug in 4 for x, so 3, 4, we would get, let's see, that'd be 2 plus 2 is 4. So that'd give me this point right here. And then eventually, so I'd have to go up to x equals 9, but eventually, and this isn't going to be to scale, I'd hit this blue line over here, right? So we're going to go ahead and make point that this is just, this would be 9, 5. All right, and so then the region I'm looking for is this region right in here. Okay, so we're going to take a slice parallel to our axis of rotation, which tells me this is a vertical slice. It's going to be a dx integral, right? And we can write this as v equals the integral from, let's see, so this happens at x equals 1. So this is going to be from 1 to 9 of 2 pi times, now we're to the right of our axis of rotation. So that means this should be x minus c, where c is going to be -1. So this is x minus -1 times top minus bottom. So that would be 5 minus square root x plus 2 dx. Okay, and then I think there's a couple of key things to keep track of here, so I'm just going to do a step real quick. You want to make sure you don't mess up this negative sign, and you want to make sure that this negative right here gets applied to everything. So we can call this 2 pi times the integral from 1 to 9 of x plus 1 times 5 minus square root x minus 2. So this would be 5 minus 2, which is 3, dx. And then from there, we can FOIL out, integrate to get an answer. And the answer that we should get is going to be 896 pi over 15. Right, and this is a pretty big number, and it kind of doesn't look that it should be that way because on my graph, this blue area is so small. But the reason it's so small is because x equals 9 should have been like way over here. Okay, and so that would have made our blue area a lot bigger. Now let's go ahead and take a look at example 5. So example 5 will give us some good practice on, okay, how do we do this when we don't have a vertical axis of rotation? How do we do this when we have a horizontal axis of rotation? Okay, so we have our xy plane. We're going to have y equals x squared. Alright, so y equals x squared. Oh yeah, I'm making that one green, this one blue, and this one purple. Alright, then we have y equals 2, which is going to look something like this. And x equals 0, which would look like this. And as a reminder, we're going to be rotating about y equals 3. So that's going to be this line right here. I'm redrawing this. This is awful. This isn't too much better, but I was about to say it couldn't have been too much worse, but it almost kind of is. Alright, whatever. So this is our region. And we're going to rotate about this line. Okay. So in this case, we're still taking slices parallel to our axis of rotation. So our slice looks something like this. That's not even straight. Okay. Looks something like this. Much better. Alright. So our integral formula, remember this is going to be v equals the integral from a to b of 2 pi absolute value y minus c f of x minus g of x dx. And so let's go ahead and look at, okay, what are these things? Well, this means that we have our lower y value, which is seen here at a value of y equals 0, to our upper y value, which is going to be bounded by this y equals 2 line, of 2 pi times, okay, absolute value y minus c. This is saying that we're taking some point, right? Let's say I take this point right here, and I want to know its distance from my axis of rotation. So this point looks something like x comma 1, whatever that x value is. And this point right here is going to look something like x comma 2, if I drew a straight line right here, which we're going to imagine I did. Sorry, x comma 3, because this is on the line y equals 3. And now I've destroyed the green curve. There we go. And so the distance between these 2 points should be 2. And we get that by doing 3 minus 1. So it should be 3 minus whatever the y value is of the point in our region. So this absolute value of y minus c, remember this is y equals 3, so our c is 3. This absolute value of y minus c becomes 3 minus y to make sure that we get a positive number. And then our f of x minus g of x, remember this is right minus left because we're going to be doing what I messed up, which was a dy integral. So this should be our right function, which is the green function. So x squared. Whoa, okay. But x squared doesn't work because we're supposed to have a dy integral. So what I'm going to go ahead and do real quick is we're going to rewrite y equals x squared as plus or minus square root y equals x. And this is kind of a point I was talking about earlier. I don't need plus or minus square root y equals x because I'm only concerned about this portion of my curve. The negative part would give this half of the curve over here. Okay. Or you could say the negative square root y would give us the left half of that parabola. The positive square root y gives me the positive half of the parabola. Or sorry, the right half of the parabola. Okay. So then this is f of x, which we now have written as square root y, minus g of x, which is given by this line, this purple line. Okay, and that's going to be x equals 0. So, 0, dy. Okay, so then this would give us, so I'm going to go ahead and do this one out just because I haven't done a dy one out for the cylindrical shell method. This would give us the integral from 0 to 2. Sorry, let's pull out the 2 pi of 3 minus y times y to the 1/2 dy, which is equal to 2 pi times the integral from 0 to 2 of 3y to the 1/2 minus y to the 3/2 dy. So then we get 2 pi times, so integrating the y to the 1/2 part, we add 1 to that, we'd get 3/2, so this is y to the 3/2, and then multiply by the reciprocal, so multiply by 2/3. But we can't forget the 3 that we initially had, so this is 2 times 3 over 3, right? So what we had is we had 3y to the 1/2, I added 1 to the exponent, so we get 3y to the 3/2, and then we multiply by the reciprocal, which is 2/3, minus, now I'd have y to the 5/2 and multiply by the reciprocal. And we're evaluating from 0 to 2. So this is going to be 2 pi times, alright, so these 3's cancel, that's nice. Plugging in 2 for y, that would give me, okay, so it's going to be 2 cubed, and then we take the square root of that. So that would be 8, the square root of 8, which is 2 root 2. So this is 4 root 2 minus, now I'd have 2 to the 5th, which is 32. And so that would give me, let's see, so we'd have 2 square root 32. Alright, well, I can factor a 4 out of that twice. So that'll give me 8 root 2 over 5. Okay. And so this would be 2 pi times 20 root 2 minus 8 root 2 over 5. right? This becomes 2 pi times 12 root 2 over 5, giving us our answer of 24 pi root 2 over 5. Okay, and that would be our volume. Now let's move on to the final boss problem. Example 6. Alright, I've kind of dreaded doing this one ever since I made it, but we're going to do it anyways. Alright, we're revolving around y equals 9. We're given these two curves. Okay, so the unfortunate thing here, I think that's the word I'm allowed to use, is that we have to complete the square on both of these. So this is y equals x squared minus 6x. So we'd get y equals x minus 3 squared minus 9. And then we'd have y equals 4x minus x squared. Implies that this would be y equals negative x minus 2 squared plus 4. Okay, so now I'm going to make the graph. What I'm going to do here is I'm going to go by 2's to, no pun intended, I'm going to go by 2's to make this a little bit easier to draw. So this is going to be 2, 4, 6, 8, 10. So now I can draw my y equals 9 line right here. Right? And the first thing I notice here is that doing the method of cylindrical shells means that we're going to have a horizontal slice, and so we're going to have a dy integral. So both of these functions, the green one and the blue one, are going to have to be rewritten as x equals something. That's just the first problem here. Okay. Now let's draw our curves. So one of them is going to go down 9 and to the right 3 and open up to the top. 2, 4, 6, 8, 10. And let me just remind myself, just by doing this real quick, that we're going by 2's. Okay. Now we need to go over 3. 1, 2, 3. And I'm not going to go by 2's on this one, so it's just going to make the scaling really weird. So this should be 3, negative 9, so something like that. If I plugged in 2, I would get 8, so it looks something like that. If I plugged in 1, I would get, that'd be negative 2 squared, which is 4 minus 9, so negative 5. Oh no. This is going to look awful. It's okay. Looks something like that. Plus or minus a lot of accuracy. And then our blue one, that's going to be downwards facing. It's going to go up 4 and to the right 2. So that's like right there. And then, let's see. We plug in 1. So that would give us 3. If I plugged in 0, that'd give me 0. There's 4, there's 5. If I plugged in 5, this would give me 3 squared, which is 9. We have to take the negative of that. So that's negative 9 plus 4 is negative 5. Oof, that's going to meet up perfectly right there. So here's the nice things that happened here. We got really, really nice intersection points. This could have gone really, really bad, really, really quick. Okay, but we got nice intersection points. Okay, now let's look at this. We need to write these as x equals something. For the green curve, that means we're going to have y equals x minus 3 squared minus 9. I'm going to add 9 over and then take a square root. So this is going to be y plus 9, take a square root, equals x minus 3. So then I'd have to add 3 over. Right? So this becomes the square root of y plus 9 plus 3 equals x. And then the only thing that I'm missing is the plus or minus on my square root. Again, this plus or minus tells me if I'm taking the right half or the left half of this parabola. The negative being the left half, the positive being the right half. Okay. Now, let's look at the blue one. So the blue one is going to be, let's see, we have negative x minus 2 squared plus 4. So I'd have to subtract over 4 and then multiply by a negative 1. So that's going to be negative y minus 4 equals x minus 2 squared. To rewrite that, that's negative y plus 4 equals x minus 2 squared. I can now take a square root, do my plus or minus, and then add over the 2. Okay, I've gotten things in terms of x. Now let's take the next difficult part. What I'm going to do here is I'm going to start, I guess, kind of boxing these off. I'm going to now make this the plum color. And so that's going to be represented by this equation right here, right? Because negative gives us the left half. And then we'll hang on. That's going to be represented by taking the negative on this function right here. So if we got rid of that positive, if we change this to a negative square root, negative y plus 4 plus 2, that would be our function for this plum colored part. Okay. And then we'll let the blue part, we'll let that stay as the positive. Now for the green one, I'm going to change this left half to purple. And so this would be represented if we chose the minus right here instead of the plus. To make this a little bit more clear, I'm going to give us a little bit more space between the plus and minus. Right. So if we choose the minus, that's given by purple. If we choose the plus, that's given by green. Right. And remember that our integral is supposed to be right minus left. So what I see here is that if I do right minus left right here, then that's going to be green minus purple. Okay. If I do right minus left right here, that's going to be blue minus purple. If I do right minus left right here, that's going to be blue minus plum. So what I need to do is split this into 3 sections. Right? We're going to call this top. We're going to call this middle. And then this part is going to be bottom. And that includes this area in here as well. Okay. So let's do these integrals. These are going to be integrals that you can do them by u substitution. You can absolutely do them by u substitution. And I think it would be great if you spent some time and tried to do these integrals that I'm about to write out. However, I don't know that it's completely reasonable to do them. Meaning, if you try on it, you can't get anything, definitely come to me, and I'm going to show you how to do it. Because it's not exactly something that you just, see right away. So our top, let me use this color. This is going to be given by the integral from, so let's see, this y value is 0, and the top y value is 4. So this is the integral from 0 to 4 of 2 pi times, now, what is nice is that for all of these, no matter where my point is, if it's in top, if it's in middle, or if it's in bottom, this absolute value of, this should be absolute value y minus c, right? So ours is y equals 9. So we're always going to do 9 minus our y value, right? Because something like this, maybe it has a y value of 3. If I want to get the distance from this point to the orange line up here, right, if I want to get this distance, this is going to be 6, and we get that by 9 minus 3. So it's going to be 9 minus our y value. Then we'll have the nasty part, which is right minus left. So this is going to be square root negative y plus 4 plus 2, right, because the right side is blue. So that means I take the positive. And then minus, now the left side we take a negative, so this is going to be negative square root negative y plus 4 plus 2 dy. Now what's nice here, when you go to start trying to do this integral, let me make this a little bit nicer so that we know that it's the upper integration limit. What's nice is that this and this will combine, right? It's going to be the square root of negative y plus 4 plus the square root of negative y plus 4, which is 2 square root negative y plus 4. And then when this negative right here distributes, you'll get a 2 minus 2, so those 2's will cancel out. It's still a rough integral. And then for the middle, we should have, let me scoot this down just ever so slightly so I don't run into that integral above. Okay. All right, for the middle, we should have, sorry, I just had some technical difficulties with my pen. We should have, all right, so we're going to go from, where was the cutoff for middle? The cutoff for middle was right here. That's at a y value of negative 5. So we need to go from negative 5 to 0, because that was the y value right here, of 2 pi times 9 minus y. This part isn't going to change, however, this will. This should be blue minus purple. So this is going to be square root negative y plus 4 plus 2 minus negative square root y plus 9 plus 3 dy. This integral is the worst because these two don't combine and your constant doesn't get canceled out. And then finally we'll have bottom, which is going to be the integral from negative 9 to negative 5 of 2 pi times 9 minus y times green minus purple. So green minus purple will give us square root y plus 9 plus 3 minus negative square root y plus 9 plus 3. So just like the top integral, the square roots combine and the constants will cancel out. Now, that is one way of calculating it. let's look at another way of calculating this that is significantly less awful. What I'm going to do is zoom out just barely so that I have room to write this, because I can actually write this one pretty much all in one line. So this is going to be the washer method. Now the washer method says that I'm going to take my cross section perpendicular to my axis of rotation. Well, my axis of rotation is horizontal, so a cross section, let's use the pretty color, looks like this. Okay? I'm going to get rid of that because it's destroying everything I wrote on there. But our cross section is going to be vertical, which means we have a dx integral. And so it means I don't have to rewrite these functions. It's just going to be the 4x minus x squared, because that's the blue, the top curve, minus what the green curve was, which was x squared minus 6x. Right, so, well, I mean, it's a little bit more than that. We need to do washer, right? So, to do a washer, we need to get an inner and a outer radius. And so it should be the integral from, the integral from our x value that goes the furthest to the left, which is 0, to the x value that goes the furthest to the right, which is 5. So we've got the integral from 0 to 5 of pi, times r out. Right, so now I'm trying to calculate the outer radius. So what we're going to have is we want to find the distance from here to here. And so that's going to be, right, and then we have to square it. So it's going to be 9 minus the green curve. So 9 minus x squared minus 6. I get that written down before I forget. 9 minus x squared minus 6x. And then we square that, because it's supposed to be r out squared minus r in squared. Right? And so then this one's going to be 9 minus the blue curve, which was 4x minus x squared. Let me just make sure I got that blue curve right. Yes, it was 4x minus x squared. Right. And so, we'd have to split it up into 3 sections. We'd have to rewrite stuff as square roots. We'd have plus and minuses. Even like calculating this integral as compared to calculating any of the top, middle, or bottom integrals, the difficulty level is way easier on the washer. Okay? So there's everything about the washer that we did is easier than the method of cylindrical shells. This is your example, this is your shining moment of why you don't always just say, well, I'm just going to do cylindrical shell method, and that's it. Okay? Probably for the questions that I give, I'm saying this probably like 80% probability. Probably for the questions that I get, you could master one of these methods, master integration, and then you'd be perfect to just use that method all the time. However, it's not reliable, right? It's certainly not recommended. But when you calculate this washer method, it'd be the same thing as calculating top, middle, and bottom and adding them together. What you will get is 2,875 pi over 3. Okay, that will conclude the end of the cylindrical shell method, and next time we will work on work.